Okay, starting.
Mhm.
All right, welcome back. Today we are going to be talking about what is a topology. Um, so let's get straight into it. So we're going to start off with X being our set, and we are going to define um, uh, the. I'm gonna draw it like a tau, but this is going to be like sort of a script T. Or you could use tau, but my professor sort of didn't like that, but I'm not good at drawing script T's. This is going to be a set of subsets of X satisfying the following three properties. The first property is that the empty set and X are going to be elements of T. The second is that if I have a family of sets with a family of sets that comes from T, right? Then the union of this family is going to also be contained in T, right? So I can take a union of, say, uncountably infinitely many sets in T, right? And I would still end up with a set in T. On the other hand, the third condition says that if I have two sets in T, then A1 intersect A2 is in T. So this is a lot weaker, right? And this can actually be generalized to show that if I can take an intersection over finitely many a sub I, where each a sub I is going to be in T, right? This is also going to be in T, right? And you can prove this by induction, actually. Right? This X is a topological space with topology T. And we are going to call the elements of T, these subsets of X, which satisfy these properties, the elements of the topology are going to be called open sets. And this is strictly just definition. That's what we call open sets. So let's give some basic examples first. There is not B. There is the discrete topology, and this topology is where every subset of X is open, right? So T contains, the topology contains every subset of X. And so obviously, these unions and intersections are going to stay in T, and then obviously we're going to have these two, empty set and X, right? And so this is sort of like the most general topology, and this is, it's not very mathematically interesting, but this is just one of the things we can define right away. On the other hand, you can define the trivial topology, where your topology is just the empty set in X, right? And this satisfies properties 2 and 3 because the unions of empty sets are going to be empty sets, and if you have an X in there, then that union is just going to be X. And then if you intersect an empty set with anything, you're going to get an empty set, and if you intersect an X with an X, you're going to get an X, right? So this is also a very simple topology. Again, not very mathematically important, but it is an example nonetheless. There's something called the cofinite topology, or sometimes the finite complement topology, where the elements of T either A is the empty set, right, because we need the empty set in our topology, or the complement of A is finite, which is why it's called the cofinite topology, right? And so this is definitely more mathematically interesting, and so it's important to prove that this is going to actually define a topology. We can show that it verifies the first condition, right? So it has the empty set, and then it's going to have X because the complement of X is the empty set, which is finite. And then as far as these unions, right? If I take a complement, so with the unions, we can sort of ignore the empty sets in the unions. They're not going to count for anything. And then if I take the complement of a union, I'm going to get an intersection of the complements, and an intersection of finite sets is going to be finite. And then similarly here, this intersection, if I take the complement of this intersection, I'm going to get the union of the two complements, and the union of two finite sets is going to be finite. We can't say the same about a union of infinitely many finite sets. That may be infinite, but certainly the union of two finite sets is finite. So this does, in fact, define a topology. The next thing we're going to talk about are some topological operations on sets. The first and most important one, well, I would argue it's not as important as something called the closure, but we'll get to that next time, is the interior, which is defined as elements, points in X, such that there is some open set containing P and contained in A. So what does this mean, right? This is saying that the interior is a subset. It's the way we've defined it is a subset of X, but clearly this has to be a subset of A, right? And you can prove that, right? But it's saying that the interior consists of points where I can find an open set that is contained in A. Now, the exterior, A exterior, is defined, well, there's a different definition in the text, Sweston, but I'm just, for lack of simplicity, it's really not that important of an operation in the long run. But since it's in the text, I might as well talk about it. But you can just define it as the interior of the complement of A. But yeah, it's kind of a useless thing. And then there's the boundary, AB. And this is going to consist of points P and X, such that for all open sets containing P, the open set contains a point in A and a point in X minus A. So again, these words interior, exterior, and boundary are sort of used in the intuitive sense, right? So with this interior, it's saying you can find, you're taking points where these open sets are going to be surrounding this point, and it's contained in your set, right? On the other hand, this boundary is, again, if you draw like a circle, right? You can think of the boundary as being, okay, no matter what open set I pick, I'm always going to have points on in A and points outside of A. You can never have it completely contained in A or completely contained in X minus A. And then following this, you can prove that these three sets form a partition of X. So what that means is that the union of these three sets equals X. However, if you take any two of these sets and intersect them, you will get the empty set. So what this means is that every element of X has to be in one of these three sets, but it can't be in more than one. So every element of X is in exactly one of these three sets. So this forms a partition. Partition of X. So again, you can sort of see this forces the exterior to be sort of boring, because the interior and boundary are used way more often, and if you know the interior and the boundary, then you automatically get the exterior, because it's just going to be everything else. Again, I don't know why I'm hating on the exterior, but it's really it's really useless. And then the last part of the section in the text, Sweston, is a lot of it. I think it's like theorem 71 or something. It's a lot of properties of the interior. So I'll list the most important ones. The first is that the interior itself is an open set. And furthermore, A is open if and only if A is equal to its interior, right? And here we get this sort of notion that open sets are sets where you can pick an element from A and find another open set which contains that point but is also contained in A. So this is sort of the idea of topology, is that you can sort of fit these open set. You can always find an open set which is contained in another open set. Another important property is that if A is a subset of B, then the interior of A is a subset of the interior of B. Right. The next thing is a very, very useful characterization of the interior, and that is if we let F be the family of open sets B sub lambda, so each B sub lambda is open, so it's in T, such that B sub lambda is contained in A, then the interior is going to be the union of all of these sets. So the interior is a union of all the open sets which are contained in A. You can also sort of go to show that once you prove that A interior is open, another thing you can do is characterize it as well, really this just goes for any open set. So let me, right, if B is in the topology, so if B is an open set, then B is going to be a union of P and B of sets A sub P, where A sub P is open and P is in A sub P and A sub P is contained in B, right? So for each P and B, we know that this set is going to exist. And that's sort of a fundamental property of open sets, is that we can find this open set, and then the open set itself is going to be a union of these sets. And this is a very, very important characterization of open sets and topology. The last couple of properties in this section are dealing with interiors and how they relate to intersection and closures. Intersection and unions. And let me check. I think I wrote this wrong. Yeah, I wrote this wrong. Sorry. my paper. The interior of an intersection is the intersection of the interiors. However, you can't say the same for unions. You can only say that the union of interiors is contained in the interior of a union, right? So it is possible to find a counterexample, which you should do as an exercise. So find a counterexample. Where the interior of A union B is not contained in the union of the interiors. And then the last thing gives a nice leeway into the next section on closure, which is that A interior union A boundary is equal to A union A boundary is equal to the complement of the exterior. Of course, this part makes sense, right? From the partition property, right? Of course, the interior and the boundary are going to give us everything except for the exterior. But here we can actually say that if we replace the interior with just A, we don't obviously there's a natural set inclusion here because we're replacing A interior with the bigger set A, but in fact you can go backwards, and essentially it's because A, in a sense, the boundary sort of completes A, and we'll talk about that next time, in such a way that that including the boundary, A is essentially the interior along with some of the boundary points, but not always all of them. And if you include all of the boundary points, this is going to give us what we call the closure of A, and that's what we'll talk about next time. So do you have any questions? Anything to go over again?
I'm actually clear with everything. It's very
All right, great. So again, I recommend not just for you, but for anyone watching this, to go through these proofs for yourself, because they're very important. Of course, pure math is all about proofs, and you should do the proofs yourself if you want to learn anything. So that's it for this video.